We have a quadruped robot, Pablo, executing a standard walking gait. It processes sensor data, calculates leg angles, and fires its motors. But halfway through a step, it completely freezes mid-stride and drops to the floor. The physical hardware is fine. The failure occurred in the software architecture. A slight delay in reading the gyroscope sensor forced the entire program to wait. By the time the code finally reached the motor commands, the mechanical balance window had passed. When you write one monolithic script that directly links your sensor read function to your gait planner and your gait planner to your motor commands, you create a rigid chain of dependencies. A single timing bottleneck anywhere in that chain crashes the entire system. ROS2 provides a communication middleware layer that sits between the low-level hardware and the high-level application logic. It acts as a decentralized messaging backbone. It allows dozens of independent software modules to broadcast and receive data simultaneously, without any single module needing to know who else is listening or who is sending the data. Getting a robot to walk is certainly an algorithmic challenge, but before you can run those algorithms, you have to solve the underlying communication routing problem. To see how ROS2 routes data, we need to throw out the monolithic script entirely and start with a blank grade. Instead of one massive file, we divide the robot's logic into tiny, singular units called nodes. A node is an independent program tasked with exactly one job. One node handles the orientation sensor, a second computes leg trajectories, and a third drives the motors. Because they run as separate operating system processes, they aren't wired together. They run their own localized loops. This strict isolation creates immediate fault tolerance. If a memory leak causes one process to fail, the operating system terminates that single process, leaving the rest of the robot's software untouched. If you are testing a new gait planning algorithm and it suddenly segfaults and crashes, the motor node and the hardware safety monitor node keep running. The safety monitor detects the sudden lack of input and gracefully powers down the legs. While node isolation cannot prevent a robot from falling if its balance controller crashes, it ensures the rest of the software stack remains responsive, allowing safety monitors to control the hardware. We have isolated the nodes, but to balance a quadruped, the leg controller needs orientation data from the IMU 50 times a second. We now have to establish a connection. We accomplish this using topics. A topic is an asynchronous one-to-many message channel. The sensor node acts as a publisher, posting data. The leg controller and safety monitor act as subscribers. Publishers fire and forget, pulsing packets outward every 20 milliseconds. If a subscriber is busy and misses a packet, the publisher never pauses. Unlike a standard remote procedure call, the sender and receiver never lock execution states. Every node runs its own event loop at its own maximum hardware frequency. If every subscriber disconnects, the publisher keeps broadcasting. The unread data packets are simply dropped by the system and vanish. Dropping unread messages prevents the middleware from buffering thousands of stale sensor readings, which would rapidly consume the onboard computer's memory and crash the system. By prioritizing real-time data freshness over guaranteed delivery, topics provide a robust mechanism for high-frequency data, where the latest reading is the most valuable. Not all data should be treated as a continuous, lossy stream. If you tell the motors to initiate a hardware calibration sequence, you need absolute confirmation that the command was received and executed. For discrete commands, ROS2 provides services. A service is a strict one-to-one synchronous request and reply protocol. When the client node sends a request, its execution timeline immediately halts. It blocks the thread entirely, sitting frozen while the server takes 5 full seconds to run the physical calibration. Only when the response is returned does the client unblock. This rigid, locked-step behavior is why you must never use services to request continuous sensor data. If a control node pauses its execution loop 50 times a second waiting for an IMU reply, the CPU spends most of its clock cycles sitting idle. The robot's real-time responsiveness drops to 0. Services trade execution speed for guaranteed delivery and strict confirmation. You reserve them exclusively for critical, one-off state changes. Walking a specific distance is a one-off command, but it presents a distinct problem. If a planner node uses a service to command a 2-meter walk, it remains completely blocked for the 10 seconds it takes the robot to physically cross the room. This requires a hybrid protocol called actions. Actions are built for long-duration tasks. The client node sends a formal goal to the action server, but its execution timeline never blocks. While the physical robot moves, the action server pushes structured progress updates back. The client continuously incorporates these distance markers into its ongoing logic. Because the client still actively executes code during the task, it retains the authority to intervene. At any point, the client can issue a preempt command and cancel the active goal mid-stride. If a perception node detects a sudden obstacle moving into the robot's path, it doesn't have to wait for the 2-meter walk to finish. It aborts the action instantly, applying the brakes before impact. By combining goal-oriented requests with asynchronous feedback and immediate cancellation capabilities, actions enable the complex, non-block-in control loops required for genuine physical autonomy. There is one final layer required to complete the architecture. We need a way to tune variables, like maximum motor velocity or balance thresholds, without having to recompile code or restart the operating system processes. We handle this with parameters. A parameter is a locally stored state configuration value that resides inside an individual node. When an engineer inputs a new configuration via the terminal, the node's internal parameter updates instantly. The leg controller reads the new frequency value on its next code cycle, and the physical stepping speed of the robot increases immediately. Because parameters require file parsing and localized state changes, they are strictly for configuration. You never use them to transmit continuous, high-frequency state data like changing joint angles. By pulling hard-coded constants out of the logic and into parameters, engineers can actively tune physical control loops and evaluate mechanical behavior on the fly. This brings us to the complete decoupled architecture. The entire quadruped is driven by multiple independent processes, communicating simultaneously. Nodes isolate the logic to prevent a single failure point from crashing the machine. Topics blast lossy, continuous sensor data across the network to maintain real-time hardware synchronization. Services lock execution states to ensure discrete commands are received and executed. Actions track long-running asynchronous behaviors while allowing for immediate cancellation. This system is designed to handle increased complexity through peer-to-peer discovery. Because nodes find and connect to each other automatically, the system can expand to hundreds of processes without requiring a central server to route the message traffic. An enterprise-grade platform like a Boston Dynamics Quadruped coordinates incredibly complex state machines across an expansive sensor payload. Yet the communication backbone utilizes these same core patterns to manage its data flow. The coordination of nodes, topics, services, actions, and parameters provides a structured framework for building and debugging robotic software that is modular, fault-tolerant, and capable of operating in the field.